So we'll now look into the xv6's implementation of the exec system call. Uh, so, uh, so, the exec system call gets invoked, say, from a shell in the user mode, and then eventually it would cause this particular function to start to execute. Now, this exec function within the xv6 source code present in the file exec.c essentially creates or executes the particular program. So, the exec function in the OS takes two parameters. One is the path, which is essentially the path of the executable, and the command line arguments. The command line arguments are essentially the second parameter. So, the idea here is that the path, which kind of, for instance, say /bin/ls, is the executable that you want to run or needs to be executed, and the arguments are the arguments to ls. So, for example, -l, right? So that's one of the arguments. Okay, so this is important. Now the next part at this particular point, right, is where we get a pointer to the executable file, perhaps stored in the hard disk. So, to be more precise, this function called name I converts this path, right, /bin/ls to a particular inode, right. So, inode is something related to the file systems, but for now we just abstract it, and you can essentially consider for this particular class that IP is like a pointer to the executable file ls in this example, and it is essentially a pointer uh, to the file present in the hard disk, right. So, using IP, the inode pointer, I can essentially traverse the particular file, right. So, recollect that /bin/ls is a elf file, and therefore I could essentially read the contents of the elf file. There would be the elf header, the section header, the segment header, the program headers, and so on. The way I essentially read the elf file is using this function called read I, right. So, so this function takes IP, which is the pointer to this particular inode or to this file stored in the hard disk, and in this call to read I, it reads bytes, it reads elf size of elf number of bytes and stores the result in this structure called elf, right. So elf is essentially defined by the structure elf header elf. You can essentially find this in the definition of elf header in the source code. Now, as we seen in the previous video, that elf header essentially comprises of various components, the first of which is the magic number, right, or the number which uniquely, or a string which uniquely identifies that this file is an elf file, right. So essentially any elf file has a string /xf7elf, right. So this is considered as the magic number. So the first thing we do is that we open the file, like for example /bin/ls, we read the elf header over here, and we check whether the magic number essentially matches, right. So if I go back to our example which we seen previously, notice the magic number, right. So 7f, 7f, 45 is E, L, and F, right. So this is what is essentially checked over here in the magic number. Okay, so if the magic number does not match, it means that whatever file you're trying to open is not an executable, and the function essentially terminates. Okay, but if it is a magic number, then in the xv6 OS we go about and essentially execute the process, right? So recollect that this particular function proc underscore page table p, p is essentially the process which has which has executed the system call, right? So in our example, we had the shell, which is essentially invoking fork, creating a child process, and the child process is invoking exec. So p here corresponds to the child process, right? So p is the entry in the proc structure or the process control block for the child process. So p corresponds to the proc entry for child process. Okay, now proc underscore page table essentially would return a pointer to the page table for the child process. Okay, the newly created child process pointer. Okay, so now what do we essentially have, right? So since we have the pointer to the page table, we essentially have identified the virtual address space for this particular process. Now within this virtual address space, we have to load the various segments corresponding to /bin/ls. So that is what we are essentially going to do next. So the next part of the exec system call essentially loads the program into memory, right? Now what we do is we look at the page, the program header, uh, uh, program header. What's it called? Yeah. So what we do is that we look at into the program header table, and for each program segment, we essentially decide whether we need to load it into the virtual memory or not, right? So this is essentially done as follows: for I equal to 0, and also you're initializing offset to be elf.ph offset, right? So what is this? So if I go back over here, right? So we are looking at and look at the offset. Yeah, if I go back over here and look, yeah, so if I go back over here and look at these entries, start of program header. So of course this is 0 bytes, but because this example was for an object file, a relocatable object file, but for an executable we would have some value here, and this start of program headers is what we are essentially loading into OFF, right? So from the elf header at an offset ph off, we read the offset or the pointer to the program header and store it in offset, right? So next, so we have this for loop, and this for loop will essentially continue for elf.ph number of times, right? So what is this elf.ph num? It is the number of program headers, right, present in the program header table. So the elf.ph off is the offset of program header table. Okay, right. And recollect in our example that we seen previously, we had 9 program headers. So what this means is that elf.phnum would have the value of 9 in our example. Okay. The next part within this for loop is where we load each segment into this virtual address space if it is needed, right. Lines 43 and 44 load the program header into this memory location pointed by ph, right. So ph is essentially the program header. So you're loading the program header into ph, right. And essentially, if I connect it back to our example, what we are doing is loading each row into this into ph, right. The for loop is going 9 times, and for each iteration we are loading a row into ph. Okay. And so now we do a couple of checks and load the program header, the segment into the virtual memory map, virtual address space of the child process if it is needed, right. So let's see what are the checks that is done. So we have first of all loaded a row into the structured ph, and then we are essentially seeing if the type for that program header is of type elf program load. So in our example, we see that there are only 2 program headers which are of type load. So only for these 2 rows would essentially this particular function continue, because if it is not of type program load, right, if the type is not of program load, then you just continue, go to the next program header in the for loop. Okay. So we are only loading segments which are of type load, right. So next is this thing, right. So what are we doing? So this is essentially a sanity check, which is checking if the size in memory is less than the file size. So this is a check, uh, just a sanity check to identify that the file size should always be less than no the okay the memory size should always be less than, or in other words, the memory size should, if the memory size is less than the file size, then there is a violation and you essentially terminate, right, or go to bad, which essentially does not load the program, right, it comes out or returns unsuccessfully. Now the next part is what is important. So what we have done so far is we have identified a program header, we have done some sanity checks to check whether ph size is greater than or equal to file size. We've also identified that, hey, this particular program header is of load type. Now all of this is done, and the next thing is where we need to load that particular segment into the virtual address space, right. For this, what do we do? So we first of all identify if we have enough of virtual address space, right. So this is essentially done by these 2 lines. So if ph v address plus ph memory size is less than ph v address, right, then go to bad. So what we're actually checking is that if there is an overflow, right. So if this memory size is so large that when it's added to v address, the virtual address, then it overflows and the overflow causes this result to go true, this if condition to go through, and you go to bad, right? So this is another sanity check. So finally we have this part which essentially invokes two things, two functions. One is UV malloc and the other one is load segment. Okay, so UV malloc essentially makes uh, the virtual address space grow larger, right? So what I mean by this is that it essentially adds more page tables entries to grow the page tables from its old size to the new size. Now the new size is given by the virtual address plus the memory size, right? So for example, uh, we start with the 0th location. Now the old size is essentially say 0, which is say at this point, and now we know that we want to load say the code segment, right? Now the code segment starts say from location 0 and has say 1 megabytes or so. So we need to grow, or we need to create the mappings for virtual to physical conversion, or so these mappings are created in the page tables to support up to v address plus memory size. So UV malloc essentially creates these mappings, while load segment essentially copies the program segment from disk to memory at the location uh, v address. Notice that v address is essentially specified in the program header, right? Okay, so we look into these two functions in more detail. So first we start with UV malloc and then go to load segment. So we have these two functions, UV malloc and load segment. So UV malloc essentially would create page table entries for the segment that needs to be loaded. So notice that um, the number of page table entries that are going to be created is specified by v address plus mem size. So from the current size of the process to v address plus mem size, this particular function would essentially create mappings from virtual address to corresponding physical address, right? So you can look up this particular function in um, in the xv6 code, right? So now we have essentially created the mappings, right? The next part is to be able to load segments from the ELF file into these newly created pages, which UV malloc has essentially created the mappings for virtual to physical address, right? So load segment copies the program segment page by page from the disk, from the hard disk to memory, starting from the location ph.v address, right? So program header.v address, table page by page, it will be copied from the ELF file into the physical memory, and the mappings for this has already been incorporated, right? So this function load segment takes 5 parameters. It takes page table, which is essentially the pointer to the child process's virtual address space. It takes v address, that is the start of the virtual address within this virtual address space where this segment needs to be copied. Um, it takes IP. IP is the inode pointer, that is the pointer to the ELF file um, uh, present on the hard disk. It takes the fourth parameter is ph.off offset, that is the program header offset for this particular entry, and the size in the file. So for this many bytes, segment is copied from the ELF file present into the virtual address space starting from this particular location. Okay, so by the end of this for loop, we have been able to set up the virtual address space where all the program code and data are essentially loaded. Okay, The next step is to set up the other aspects. So we would next in this example set up the stack space. Okay. Now the stack essentially is still created again using this UV malloc, and which again is creating space for which is of at least two page sizes. So two page sizes is essentially 2 into 4 KB. So we are creating 8 kilobytes for the stack. Now one thing we actually want to see over here and highlight over here is that out of these two pages, one page is used for the stack, right? So one page means there are 4 kilobytes used for the stack. The stack pointer would be initially set to the top of this address, and then as it gets used, the stack essentially grows downwards. The second page is used as the guard page. So this guard page ensures that the stack essentially doesn't overflow beyond the 4 kilobytes. So the way we essentially create this guard page is to remove the mapping for this particular page. Now removing the mapping means or preventing any read or write to this particular guard page. Now if the stack gets used and if it overflows crossing the boundary and enters into the guard page, it would result in a violation and the process would essentially terminate. So this would ensure that the stack is always within this particular page, within this 4 kilobyte page, while the program is executing. Okay. So we have now created the code, we have created a data, and we have kept the stack. We have created the stack for this particular program. What's more is that we need to pass the command line arguments. Okay. Now for the command line arguments, we would again just go back and take and just review what the command line arguments means, right. So when we have a function, say int main, int argc, char star star argv, right. So argc and argv essentially help us to pass command line arguments to our C program, right. So if my function is a.out, then something like /a.out, and I can pass parameters such as 1, 2, 3, 4, 5 and so on. Okay. So these are my command line parameters. So argv0 is a.out, argv1 is this, argv2 is this is the third argument, this is the fourth, fifth and sixth argument. argv0 is essentially this one. Okay. So how are these parameters essentially passed to this main function, right. So so first thing you notice is that argc is an integer, while argv is a pointer to an is essentially a pointer, and so argv is essentially a set is an array of pointers, right. Now these parameters are essentially passed through the stack that we have just created. Okay. So recollect now that we have the virtual address space for this process. This is the child process. We have created the code, we have created space for the data, we have created a guard page, and I am just increasing the size of the stack just to explain it better. Okay. So now this is our stack, right, and our stack pointer is going to be initially set at this particular point, right. So what the operating system does is that it receives the command line arguments from the parent process. In this case, the uh, through the exec system call. So um, recollect that when we do exec, we pass the elf executable, and then we essentially pass the command line arguments, right? So the command line arguments are essentially passed here. So when exec executes in the operating system, these command line arguments are passed to the newly created executable through the stack. So what would happen is that each of the command line arguments, just a minute, let me check if it's up to do. Yeah, each of the command line arguments, like the string dot slash a dot out, the string, this would be a string, the string 1, the second which is the argv1, argv2, argv3 would essentially be placed on the stack by the operating system, right? But this is not enough. In addition to this, the pointers to each of these strings is placed on the stack by the OS. So here we would have essentially pointer to argv0. So essentially this is a pointer to here. Similarly, we have pointer to argv1, which is this, and so on, right? And with each time we push something into the stack, we would have the stack pointer essentially being pushed downwards, right? And this is what we are essentially going to see in the exec code next, right? So this part of the exec function essentially creates this stack, right? So what we see over here from this here to here, this particular for loop is where we push the argument strings and prepare rest of the stack in the user space, right? This is the program that we want to start. So we are copying these strings like arg0, arg1, argn, and so on into the start. So these are the command line arguments. Okay, then we have a null termination which marks the end of the command line arguments, and then the command line strings, and then essentially start pushing pointers to these strings, like pointer to argn, pointer to arg1, pointer to arg0, and so on, right? A pointer to 0 and so on. Okay, so all of this is essentially done over here as well as here. Now, one important thing to observe over here is the function copy out, right? Now, copy out, it's used twice. Now, why it is important for us is that this copy out is copying into the child's virtual address space. So, recollect that we have created a virtual address space for the child, virtual address space, but in addition to that, this particular code, right, all of this exec function is essentially running from the kernel's virtual address space. VAS stands for virtual address space. So you have the exec code and so on executing from the kernel's virtual address space, and specifically what we want to do is create these arguments, the stack and so on in the child's virtual address space. So we want the data, the code, the stack and so on to be present here, right? So copying from the kernel's virtual address space to the child's virtual address space is not straightforward. It's not just simply copying from one location to another. You would need to essentially go through the page tables of the child, identify the corresponding physical address, and then copy into that physical address. So this is what is essentially done in this function copy out. It requires the page tables because it requires to know the page table for this particular child's virtual address space, and it copies directly into the physical memory corresponding to the stack pointer. Okay. So in this way, we have essentially set up the stack with the command line arguments and pointers to the command line arguments. This is our argv, right? So we are all set to go. The last part is that we need to set up a few things which are in the Trapframe, in the proc structure, and also the command, the parameters to the main function before we can actually complete, right? So one thing to remember is that when we have a function main, right, in RISC-V, the first parameter, as we have discussed, would be in the register, would be passed through the register A0. The second parameter, argv, which is essentially a pointer, would be passed through the register A1, right? A1 essentially is a pointer to this location in the stack, which contains an array of pointers to different arguments, and argc essentially tells you how many arguments are present, right? So we need to set up A0 and A1 appropriately to point to the correct address on the stack, and argc should have the right number of arguments. So this is what is essentially set over here. So by using p Trapframe A1, setting it to stack pointer, we are essentially saying that the register A1, when the program executes in the user space, that is the newly executed program in user space, the register contains A1 should essentially point to this value of SP, right? Now recollect, SP would be the bottom of the stack, that is the essentially would contain where the argv array starts, right? Similarly, the first parameter A0 would contain argc. So this argc value ends up in the A0 register and would be the first argument to main. Okay. So in addition to passing the parameters, there are other few things that we need to take care of, and yeah, one important thing is the aspect of this, right? And we see that we set p Trapframe EPC to be equal to elf.entry, right? So recollect what entry is in an elf file. So going back, we see that here is the value of entry, which is 0x4004b0, which essentially tells us where the program should start executing, right? So coming back here, right? So if we set EPC to be equal to elf.entry, it would mean that when the this newly executed program starts executing, it will start executing from this address specified in elf.entry. Okay. So we have now set the stack pointer appropriately. We have set the arguments to main correctly. We have set the program counter correctly, because this EPC value would be loaded into the program counter, so that the program counter would start executing from elf.entry, that is the entry point. Okay. The last thing we need to do is also set the name appropriately. We have created a child process. Now the child process, if we create it from the shell, the child process essentially has the name of the shell itself, but now we have executed something like /bin/ls within the child process, right? So the name should be essentially set appropriately. So the name of the child process now gets changed from shell or bash shell, for instance, to / or bin.ls or whatever. Similarly, other things like the working directory, the size, the other aspects of the proc structure should be essentially set appropriately.